Can somebody else please record it as a backup? Raise up your blue hand so I can give you permission, please. There we go. All right, I see Esmeralda. Is that for recording? All right, I'll give you, hold on. Wait, where'd you go? Could you raise your hand again, please, Esmeralda? I lost you. Oh, there you are. Okay. Allow record. Perfect.
Can you repeat that last thing we just went over so it's on the recorded section?
Yes.
Thank you.
So, yeah, thank you for remembering that. I totally forgot. We've got to make sure at the beginning of every lecture that somebody's recording it because my recording is not working. Okay. So the question was to explain intrinsic control of heart rate, which is the same as asking cardiac autoconduction. So that was the SA node, initiating the electrical signal, causing contraction in the atria, and then setting the rhythm at 100 beats per minute. Then the signal goes to the AV node, atrioventricular node, which delays the signal so the ventricles can finish filling. Then the signal goes down the AV bundle to the Purkinje fibers, which cause contraction in the ventricles. Okay. Alexis, can you please explain one type of extrinsic control of heart rate? So we have 3 different things we talked about acting on the SA node to change your heart rate.
Oh, it sets the heart rate to 100 beats per minute.
Well, that's intrinsic control. So if nothing is acting on the SA node, the SA node sets the rhythm at 100 beats per minute. That's intrinsic control. So extrinsic control is when something external is acting on the SA node to either increase or decrease the heart rate. So we talked about 3 different things that act on the SA node. And we drew that graph, remember? What's causing increases in heart rate?
Oh, is it the, oh, yeah. The sympathetic cardiac nerve?
Sympathetic cardiac nerve would act on the SA node and cause the heart rate to do what?
To decrease?
It'll increase.
Oh, increase.
Yeah, so remember the parasympathetic nervous system is in charge of everything below 100 beats per minute. So if it's active, if your parasympathetic system is active, your heart rate will be very low. Sympathetic nervous system is in charge of exercise, everything above 100 beats per minute. So if the sympathetic nervous system is active, it's going to increase your heart rate. So sympathetic cardiac nerve is part of the sympathetic system. So when it's active, it's going to increase your heart rate. Okay, Susanna, can you explain another form of extrinsic control of heart rate?
I don't know.
Okay, that's okay. Brianna Chavez, can you do one?
Decrease in vagal tone.
Okay. And what would that do to the heart rate?
That would increase it.
Good, so that's part of the parasympathetic system. If you're at rest and your heart rate is down towards 60, and you start exercising, the parasympathetic system decreases activity, decreases vagal tone, which allows the heart rate to increase. Good, and Jolena, can you tell me the third part of extrinsic control?
The third one would be the release of epinephrine, and that would increase our heart rate.
Good, act on the SA node to increase the heart rate. Perfect. So let me go back to my whiteboard.
A professor, remember you have to talk about something you forgot to talk about in last lecture.
Do you remember what it was?
No.
The vasodilation. What causes vasodilation?
Okay. Yeah, we'll get there. Thank you. Okay, so we had this graph of intensity versus heart rate, and we said a reasonable low heart rate is about 60 beats per minute. A reasonable max heart rate is about 200. As intensity increases, heart rate increases. We know that's linear. And then we put across here the 100 beats per minute. Significance of that is that that's the natural sinus rhythm. And then we said increases between 60 and 100 are due to, increases in heart rate between 60 and 100 beats per minute are due to what? If anybody can chime in here with an answer, please.
Can you ask the question one more time?
Decreased PNS.
Yes, increases in heart rate between 60 and 100 beats per minute are caused by what?
Decrease in vagal tone.
Decreased, yeah, parasympathetic nervous system activity, specifically decreased
Vagal tone.
vagal tone. Good. And then these increases in heart rate above 100 beats per minute are due to what?
Increased SNS.
Increased sympathetic nervous system activity, specifically
Sympathetic.
sympathetic cardiac nerve and
Epinephrine.
epinephrine. Okay, I'm abbreviating that. Make sure you know what it stands for and how to spell it. Okay, so this is extrinsic control of heart rate. The three things that are acting on the SA node to cause it to increase or decrease. Okay, this is specifically during exercise, so it's an increase. Intrinsic control of heart rate is just the SA node controlling itself, setting you to 100 beats per minute. Extrinsic control is something external acting on it. Okay, any questions on intrinsic or extrinsic control of heart rate? Okay, then, so the intrinsic control of heart rate we also called cardiac autoconduction. Okay, so intrinsic control of heart rate and cardiac autoconduction are the same thing. You'll explain the SA node, the AV node, the bundle, and the Purkinje fibers. Okay, then we talked about intrinsic and extrinsic control of blood flow. So we're talking about blood flow, we're talking about the arterioles. Okay, so Heather, can you please explain extrinsic control of blood flow?
You said extrinsic control of blood flow?
Correct. That means something external is acting on the arterioles.
Is it the SNS and external factors that are acting? No,
Yeah, that's part of it. Just want a little more detail here.
Yeah, SNS and external factors acting on HR.
Okay, so if it's external factors acting on the heart rate, that's extrinsic control of heart rate.
Okay.
So I'm asking about extrinsic control of blood flow. Remember I said the two are similar, so don't confuse them. If I'm saying cardiac, we're asking about heart rate, then we're talking about the SA node. If I'm talking about control of blood flow, we're talking about the arterioles vasodilating and vasoconstricting. Okay, so what is an external factor, extrinsic, that acts on the arterioles to cause either vasodilation or vasoconstriction? You can pass it.
I'm not sure.
That's fine. Rosie, can you do that one, please?
I have vasoconstriction is caused by epinephrine.
That's all it is. Epinephrine acts on the arterioles to cause vasoconstriction. So when you're exercising, you release epinephrine. The higher the intensity of exercise, the more epinephrine you release. So epinephrine's now in your blood and it's going all over everywhere in your body, and everywhere it goes, it's causing vasoconstriction. Okay, there's one exception to that, which is what I needed to cover. So the exception to that is that the vessels near the skin. So the vessels near the skin have different receptors on them. They respond differently to epinephrine. At the vessels near the skin, epinephrine will cause vasodilation. The purpose of that is for thermoregulation. So when we're exercising, we want to redirect some of our blood flow to the skin so that we can dissipate heat and so that we can sweat. So epinephrine causes vasoconstriction everywhere except at the vessels near the skin where it causes vasodilation for the purposes of thermoregulation. Okay, vasoconstriction is active, meaning it requires a muscle contraction. So we've got the smooth muscles in the arterioles. Epinephrine will cause those muscles to contract, which will cause vasoconstriction. Vasodilation is passive, meaning it does not require a muscle contraction. You just relax those smooth muscles and the vessels dilate. Okay, they don't completely relax, because if the muscles in the vessels completely relax, the vessels would just collapse on themselves and we wouldn't have any blood flow. So there's always a little bit of muscle tone in there, but more of the contraction will cause vasoconstriction, less of a contraction will cause vasodilation, except in the vessels near the muscle, near the skin. The vessels near the skin is the only place where you get active vasodilation. So in those vessels, contraction of the muscle will cause vasodilation. Okay, so I'm gonna say all that again. Epinephrine causes vasoconstriction everywhere except at the vessels near the skin. Vasoconstriction is active and vasodilation is passive everywhere except at the vessels near the skin. Vessels near the skin, epinephrine causes active vasodilation. Okay, questions on that?
Causes active vasodilation for the purpose of temperature control, right?
Say that again.
It causes active vasodilation for the purpose of temperature control?
Yes, thermoregulation.
Thermoregulation. Thank you.
Okay, Tito, can you please explain intrinsic control of blood flow?
So the only thing I have here is the epinephrine causing the constriction. That's
Okay.
all.
Do you remember what causes vasodilation?
No, I didn't write anything.
Oh, this was the class we didn't get very far.
Yeah.
Okay, so this is what we didn't cover. Okay, perfect. So this is intrinsic control of blood flow. So we didn't cover this, right?
Right.
Okay, so, gosh, I can't believe we didn't get this far. Okay, we're really far behind. So, you're exercising, you secrete epinephrine. Epinephrine is going all around in your body causing vasoconstriction. But let's say you're riding a bike. You need an increase in blood flow to the exercising muscle, but the epinephrine is causing vasoconstriction. So we need vasodilation, okay? We vasoconstrict in areas where we want less blood flow. We vasodilate in areas where we want more blood flow. So we need vasodilation at the exercising muscle, okay? So the vessels can do that themselves. I'm gonna put the whiteboard back on. So what happens is, at the exercising muscle, the muscle is consuming oxygen, right? The more the muscle is exercising, the more it's going to consume oxygen. So the blood in the vessels surrounding the muscle are going to be low in oxygen, okay? The exercising muscles are producing carbon dioxide as a byproduct, right? So there's going to be high levels of carbon dioxide at the exercising muscle. The exercising muscle is also producing lactic acid. So there will be high levels of lactic acid. HLA is the abbreviation for lactic acid. And therefore, there will also be high levels of hydrogen from the lactic acid. Okay? Because of the bicarbonate buffer and all of this lactic acid, oh, we also have that, we already have the high levels of carbon dioxide. So we will have low pH. Remember, the blood will become more acidic because of the hydrogen and the carbon dioxide. So that's a lower pH. And we will have a higher temperature because the muscle is also producing heat. So these are conditions you'd expect to see at the exercising muscle. So we call those local conditions. Let me write that here. Local conditions at the exercising muscle. Okay, so what sensory receptor senses chemical changes in the blood? Anybody remember?
Receptors.
What is it?
Chemoreceptors?
Chemoreceptors. Okay, so chemoreceptors sense chemical changes in the blood, such as these. So it's going to send that information in, which is going to trigger vasodilation in these arterioles. That vasodilation is going to bring in more blood flow. Okay, so if we bring in more blood flow, we bring in fresh blood to this area, That's going to bring in more oxygen. It's going to clear out the carbon dioxide and the lactic acid and the hydrogen. It's going to normalize the pH and normalize the temperature. So is this positive feedback or negative feedback?
Negative.
Because the stimulus is all of these local conditions. Chemoreceptors sense that, and the response is to vasodilate and bring in more blood. When the blood comes in, it clears out all of these conditions. So it's a negative feedback loop.
Oh,
Okay. But this is how we trigger vasodilation to increase blood flow to the exercising muscle. Okay, so we have epinephrine going through our blood everywhere it's going, except for the skin. It's trying to cause vasoconstriction. But at the arterioles near the working muscles, these conditions are occurring. They're being sensed by the chemoreceptors and causing those vessels to dilate. So we're getting vasodilation in these arterioles, even though there's epinephrine trying to cause vasoconstriction. Okay, that's called sympatholysis. So sympatholysis is when we're able to get vasodilation in the arterioles, even though epinephrine is trying to cause vasoconstriction. Okay, I'll say that again. Sympatholysis is when we're able to get vasodilation in the arterioles at the exercising muscle, even though there's epinephrine there trying to cause vasoconstriction. So you can kind of think of it as a battle between the intrinsic control of blood flow and the extrinsic control of blood flow. Okay, epinephrine's trying to cause vasoconstriction in the arterioles. The chemoreceptors are trying to trigger vasodilation in the same arterioles. So we have this battle going on. Okay, the chemoreceptors have to win that battle. The intrinsic control has to win that battle so we can bring in blood flow to the muscle. Otherwise, we wouldn't be able to increase blood flow to the exercising muscle. We wouldn't be able to exercise. Okay, so we have to be able to get vasodilation at the exercising muscle. Okay, so
get vasodilation in the arterioles?
In the arterioles of the exercising muscle.
Okay.
Yes. So we had, remember we had this drawing of the vessels. Here is the muscle, and these are the arterioles, right? Delivering the oxygen to the muscle. So if we vasoconstrict these arterioles, we'd get less blood flow here. And epinephrine is trying to vasoconstrict there. But because we have all these conditions happening right here, that's going to cause these vessels to dilate, which is going to bring in more blood flow. Okay, so we have two things trying to act on the arterioles. One of them has to win. So that battle is the sympatholysis. Okay, so that means we had intrinsic and extrinsic control of blood flow, talking about what's happening at the arterioles. So the arterioles control blood flow. So extrinsic control of blood flow is the epinephrine acting on the arterioles, trying to cause vasoconstriction. Intrinsic control of blood flow is the vessels deciding on their own to vasodilate based on those local conditions. Okay, chemoreceptors sense those local conditions, trigger vasodilation. Okay, you need to know those 6 local conditions and be able to explain why they're happening. Why are oxygen levels low? Why is carbon dioxide levels high? Why is pH low? Okay, you need to be able to name and explain those. Okay, don't confuse that with the intrinsic and extrinsic control of heart rate. If we're talking about controlling the heart rate, we're talking about the SA node. If we're talking about controlling blood flow, we're talking about controlling the arterioles. Okay, another term for what we just covered with the intrinsic control of blood flow, another term for that is arterial autoregulation. That should be one word. Arterial autoregulation is the arterioles controlling themselves. Kind of like cardiac autoconduction is the heart controlling itself. Arterial autoregulation is the arterioles controlling themselves. So arterial autoregulation is the same thing as intrinsic control of blood flow. Okay, blood flow has to do with arterioles. Cardiac has to do with the heart rate. Okay, questions on intrinsic or extrinsic control of blood flow? We're good? So we hadn't talked about blood pressure yet at all, right?
No.
Okay. Woo, brace yourself, it's gonna be a lot. Okay, so I gotta give you a definition, first of all, of blood pressure. Blood pressure is the pressure exerted by the blood on the walls of the vessels.
Actually, I feel like you might have mentioned some of this as far as the definition for blood pressure and the formulas for it.
Did I give you the peripheral resistance? Did we talk about peripheral resistance?
Yeah.
Definition for blood pressure and peripheral resistance, but you stopped there and said we didn't talk about vasodilation.
Okay. Okay, so we talked about blood pressure, thank you, equals cardiac output times peripheral resistance. Yes, and we said peripheral resistance equals length times viscosity.
Was there a definition for peripheral resistance? You gave us the formula, but I don't see a definition.
Of peripheral resistance?
Yeah.
I don't really give a definition of peripheral resistance. You can think of it as resistance to blood flow in your extremities, basically, if I had to come up with a definition. Resistance to blood flow. So if resistance is high, it means it's difficult to get the blood to flow. If resistance is low, it's easy to get the blood to flow. Okay, so did we go over length and viscosity, just not radius? I don't remember where we finished.
I think you mentioned radius as well.
We did do radius, yeah.
We talked about the straws and the different length of the straws and the different thickness.
Yes, yes.
And did we talk about vasoconstriction and vasodilation, changing the radius?
We stopped at vasoconstriction. It was just vasodilation that you didn't get to.
Okay, so.
What is peripheral resistance equal to? Like what is L, V, and R4?
Peripheral resistance equals the length of the vessel times the viscosity of the blood divided by the radius of the vessel to the fourth power. Okay, so length of the vessel, we talked about drinking through a 6-inch straw versus drinking through a 6-foot straw. The longer the vessel, the higher the resistance. Okay, it's harder to get the blood to flow through if the vessel is longer, right? Viscosity.
Viscosity of what?
Viscosity is how thick the blood is. So we said, so an increase in the length of the vessel would cause an increase in peripheral resistance. An increase in the viscosity or thickness of the blood would also cause an increase in resistance. But radius has an inverse relationship to resistance. So as the radius gets smaller, the resistance goes up. As the radius gets larger, as the vessel dilates, resistance goes down, right? The wider the straw, the easier it is to get the blood flow through. The narrower the straw, we talked about the teeny tiny red straw, right? The narrower it is, the more resistant it is to blood flow. So a decrease in radius means it's getting vasoconstriction, causes a decrease in radius, which increases resistance. Okay, everybody okay with that?
Yep.
Questions? Go ahead if you have a question. Okay, okay. So what I'm going to do then is I'm going to go in a little more detail to the blood pressure. So we have two versions of the blood pressure formula. We have the short version, which is blood pressure equals cardiac output times peripheral resistance. And then we can expand the cardiac output and expand the peripheral resistance. So the expanded version of the blood pressure formula would be blood pressure equals heart rate times stroke volume times length times viscosity over radius to the fourth. Okay, so I'm going to take that expanded formula and I'm going to spread it out across the page and add a lot more detail to it. So you need a whole page for this. So I'm going to erase this. Okay, and I'm going to write across here, big, blood pressure equals, sorry, it puts those dots in there when I do two spaces. The dots don't mean anything. Heart rate times stroke volume times, times I'm just going to do, sorry, I'm going to do L times V and assume that you know what that stands for. Divided by radius to the 4th. Okay, so these two together make up cardiac output. This all together makes up peripheral resistance. Okay, so what we're going over now is details of how we control blood pressure. Okay, so as we increase our intensity of exercise, our blood pressure is going to increase. Specifically, our systolic blood pressure is going to increase. Okay, so that increase in blood pressure is going to be caused by increases in cardiac output and increases in peripheral resistance. Okay, in order to get increases in cardiac output, we're going to have increases in heart rate and increases in stroke volume. And in order to have increases in peripheral resistance, okay, if you looked at length and viscosity and radius, those are all things that contribute to peripheral resistance. If we can only pick one of those, which one is going to contribute the most to changes in peripheral resistance? What do you think?
Viscosity.
No.
The radius.
The radius, because the radius is to the 4th power. So very small changes in radius will have a larger influence on peripheral resistance than length or viscosity. So most of the time when we're talking about peripheral resistance, changes in peripheral resistance, we'll be talking about changes in radius. Okay, so in order to get an increase in peripheral resistance, we're going to need a decrease in radius because they have an inverse relationship. Okay, so we're going to go back and talk through each one of these things. What's causing the increases in heart rate during exercise? What's causing the increases in stroke volume? And what's causing the decreases in radius? Okay, so starting with heart rate, we talked about 3 things that cause increases in heart rate during exercise, and they all have to act on something. What's the effector that controls heart rate?
The SA node.
The SA node. So I'm going to put that here. I'm going to make it a little bit smaller. SA node is the effector here. And I'm going to put a box around that to identify it as the effector. Okay. Then we talked about 3 different things that act on the SA node that cause increases in heart rate during exercise. What are they?
The epinephrine, the vagal nerve, and the sympathetic cardiac nerve.
Yep. So I'm going to put them in this order. I'm going to do epinephrine here. So is it an increase or a decrease in vagal tone?
Decrease.
A decrease in vagal tone will cause an increase in heart rate. Okay, that decrease in vagal tone is caused by decreased parasympathetic nervous system activity, right? As a response to exercise. Okay, so you start exercising, that causes the parasympathetic system to withdraw, starts to decrease the parasympathetic activity, which is going to decrease your vagal tone. That's going to act on the SA node and cause an increase in heart rate. That increase in heart rate will cause an increase in cardiac output, will cause an increase in blood pressure. Okay, everybody follow that sequence of events? Okay.
Can you explain that one more time? I'm sorry.
Yes. So you start exercising, that causes the parasympathetic nervous system to decrease its activity. That's going to decrease vagal tone, which is going to have an effect on the SA node that causes the heart rate to increase. That increase in heart rate will cause an increase in cardiac output, which will cause an increase in blood pressure. Okay, so once again, it's a series of events. This causes this, causes this, causes this. Okay, what else goes here as the third thing that acts on the SA node? We have the vagus nerve, we have the epinephrine, and what's the other thing?
Sympathetic cardiac nerve.
Sympathetic cardiac nerve. Is that part of the sympathetic or parasympathetic nervous system?
Sympathetic.
Okay, and is the sympathetic nervous system increasing or decreasing its activity during exercise?
Increase.
Good. So this is increased sympathetic nervous system activity as a response to exercise. Okay, so you start exercising, that increases your sympathetic nervous system activity, which acts through the sympathetic cardiac nerve to act on the SA node to increase your heart rate, which increases cardiac output, which increases blood pressure. We okay with that? Okay, stop me if you have a question. The epinephrine is also acting on the SA node. Is that part of the sympathetic or parasympathetic system?
Sympathetic.
Okay, that's due to increased sympathetic nervous system activity as a response to exercise. Okay, so you start exercising, that increases your sympathetic nervous system activity, which causes the release of epinephrine. That acts on the SA node to cause an increase in heart rate, which causes an increase in cardiac output, which causes an increase in blood pressure. Okay, so none of this is new information. This is extrinsic control of heart rate. These three pathways explain the increases in heart rate during exercise. Okay, all we're doing here is linking that to blood pressure, because the increases in heart rate will cause an increase in cardiac output, will cause an increase in blood pressure. Okay, so this is explaining the three ways that heart rate is increased during exercise. Okay, any questions on this? Okay, for stroke volume, what is the effector for stroke volume? Anybody remember what controls stroke volume?
The left ventricular myocardium.
Yes, left ventricular myocardium, remember, is just the muscular wall of that left ventricle. So if we can get that muscle to contract more forcefully, we can get more blood out with each contraction. That's an increase in stroke volume. Okay, so the left ventricular myocardium is going to have an increase in contraction strength. Okay, I'm going to mark the left ventricular myocardium as my effector. If we can get that to increase contraction strength, then we can get an increase in stroke volume, which would cause an increase in cardiac output and an increase in blood pressure. So what do you think acts on the left ventricular myocardium to cause it to contract more forcefully? I'll give you a hint. It's a hormone that's released during exercise that affects almost everything. What hormone would that be?
Epinephrine.
Epinephrine. If you ever have to guess about what's causing something during exercise, epinephrine is usually a good guess. Okay, so the release of epinephrine is going to act on the left ventricular myocardium, causing it to contract more forcefully, increasing stroke volume, which increases cardiac output, which increases blood pressure. Okay, that epinephrine is released as part of increased sympathetic nervous system activity as a response to exercise. Okay? Okay, let's go to radius. What controls the radius? If we want to change the radius of the vessel, what do we have to act on?
muscle?
Radius of the vessel is how wide or narrow it is. What controls that?
Viscosity.
Is it the chemoreceptors?
Well, the chemoreceptors are acting on this. We either need vasodilation or vasoconstriction to affect the radius, right? What vasodilates and constricts?
Arterioles.
The arterioles. Okay, so the arterioles. Sorry, I want to put that, move that up a little bit and make it all caps. So the arterioles are the effector for the radius. Okay, if we're going to get a decrease in radius, what do the arterioles have to do? Vasodilate or vasoconstrict?
Constrict.
Okay, so vasoconstriction. Let me try to move that up a little bit. So we need the arterioles to vasoconstrict. It's not letting me move it. There we go. We need the arterioles to vasoconstrict in order to get the decrease in radius. What do you think is going to act on the arterioles to make them vasoconstrict? Take a guess. Epinephrine is involved in almost everything related to exercise. Okay, that epinephrine is released as part of increased sympathetic nervous system activity. Oops. Increased SNS activity as triggered by exercise. Okay, so this big mess of a drawing is a detailed explanation of how blood pressure increases during exercise. Okay, it's acute control of blood pressure, how we get blood pressure increase during exercise. So notice all of the pathways at the bottom start with exercise. And then that exercise triggers several different events that are going to act through either heart rate or stroke volume or radius to cause an increase in cardiac output or peripheral resistance, which is going to contribute to increases in peripheral resistance. Okay, but there's a lot of overlap in these pathways. There's a lot of repetition. So we can simplify this map, okay, so that we're not repeating as much. All of the pathways start with exercise. How many unique pathways do we have coming off of exercise? Two. What are they?
One is exercise to decrease peripheral nervous system activity, then
parasympathetic.
Parasympathetic nervous system activity. Then it decreases vagal tone, affecting the SA node.
Okay, hold on. Just go to one step above exercise. So start exercising. We have two ways of responding, either through decreased parasympathetic activity or through increased sympathetic activity. Does everybody see that? So from exercise, there's only two options of where to go. The parasympathetic side just has one pathway that goes to increasing heart rate. How many different branches does the sympathetic side have?
4.
What are they?
Would it be the sympathetic cardiac nerve, the
And,
RFB, and then the arterioles?
but the arterioles still going through epinephrine. Okay, so just going one step past increased SNS activity, we have either sympathetic cardiac nerve or we have epinephrine. Those are two options.
Oh.
Okay, sympathetic cardiac nerve goes to the SA node, goes to heart rate. Epinephrine goes how many different ways? 3. Epinephrine is going to go to the SA node, to the left ventricular myocardium, and to the arterioles. Okay, so we're going to simplify this. We're going to flip it over. We're going to put exercise at the top. So all the pathways start with exercise. All the pathways end with an increase in blood pressure. And then we're going to draw out the pathways without repeating anything. Okay, so you should have this drawn out. You can take a screenshot if you want, because I'm about to clear it. put this drawing off to the side because we're going to use the same information to build the next map, which is all the same information, just better organized. Okay, so take your screenshot if you want, because I'm about to get rid of this. Okay, so we're redrawing this concept map. On this page, before we start drawing the map, you should write the blood pressure formula. You should write both versions of the blood pressure formula. The shortened version, blood pressure equals cardiac output times peripheral resistance. And then the expanded version, blood pressure equals heart rate times stroke volume times length times viscosity over radius to the fourth. Because notice that all of these pathways are going through either heart rate, stroke volume, or radius, which are going through either cardiac output or peripheral resistance. So this whole map relates back to the formula, how we control blood pressure. Okay, so I'm going to start at the top of this with exercise. So that's what's triggering all of this. Is it matter for you guys that this is so small? Is it better if I make it bigger, or does it matter? Means it's okay? Okay, because I'm going to put a lot of information on here. So, okay, that exercise, what sensory receptor controls blood pressure? Anyone?
Baroreceptors.
Baroreceptors. So exercising will trigger the baroreceptors to send that information to the brain.
Should we write that small as well? Is there going to be a lot of stuff on this page?
This is going to, you should, yeah, this is going to fill up your page.
Okay.
So, yeah. So I need to draw the arrows in here. Exercise will trigger the baroreceptors to send that information to the brain. The brain is going to respond in two different ways. What are they? Look back to the map we just had. There were two options coming off of exercise. What were they?
The parasympathetic.
Okay, so the parasympathetic system, is it increasing its activity or decreasing its activity?
Decreased.
Okay, so this is decreased parasympathetic nervous system activity. Okay, I'm abbreviating it. Make sure you know what it stands for. It's not peripheral, it's parasympathetic. Okay, that decreased parasympathetic nervous system activity is going to cause what?
An increase in heart rate?
Not yet.
Oh.
Decreased
vagal tone.
Vagal tone is going to then act on what? What's the effector?
SA node.
If we're talking about increasing or decreasing heart rate, we have to talk about the SA node. Okay, so I'm going to box my SA node as my effector. Draw my arrow here. So decreased vagal tone will act on the SA node, and how will the SA node respond to a decrease in vagal tone?
It will decrease as well, right?
What will decrease?
The signal it sends out.
Will decrease or increase?
Increase.
A decreased vagal tone will cause an increase in heart rate. Right, because it's parasympathetic. So a decrease in vagal tone will cause an increase in heart rate, which in turn will cause what?
Increased cardiac output.
Increased cardiac output. I'm abbreviating it. Make sure you know what it stands for. Which will then cause increased blood pressure. Okay, I'm going to box this one because all of the pathways are going to lead to an increase in blood pressure. Okay, so this is the parasympathetic pathway. What was the other choice for the brain to do? Besides decreasing parasympathetic activity, we could also
Increase sympathetic.
Increase sympathetic nervous system activity. Okay, how many branches do we have coming off of this? How many different ways does the sympathetic nervous system activity act here?
4.
2.
Is it 2?
I heard 2 and I heard 4.
It's 2.
Okay, what are they?
Sympathetic cardiac nerve and epinephrine.
Good. Sympathetic cardiac nerve. Let's just follow this pathway out. What does the sympathetic cardiac nerve act on?
The SA node.
The SA node, and it's going to cause an increase in heart rate. So we could draw that its own pathway heading to increased blood pressure, but we already have that pathway written over here. So that's the benefit of drawing a map like this. We can just connect it over there and we don't have to rewrite the same pathway because all of the effects of that are the same. So the sympathetic cardiac nerve will act on the SA node, causing an increase in heart rate, which causes an increase in cardiac output, which causes an increase in blood pressure. Okay, then our other pathway over here was epinephrine. How many different branches do we have coming off of epinephrine?
2.
What is it?
3.
3. What are they?
The SA node.
SA node.
The left ventricular myocardium.
Okay, and?
Arterioles.
Good, so we have 3 different pathways here. Now, when you're drawing a concept map like this, one of the rules is that you're not allowed to cross lines. So if I know that one of these lines need to go over to the SA node on the other side of the map, I need to make sure I put that on the inside arrow. Because if I were to put arterioles on the inside arrow, that would lead to blood pressure, and then my line that needs to go over to SA node would have to cross. Okay, so I've got to do the SA node first, and I can just extend this line all the way over the SA node because the effects after that are the same. It increases heart rate, cardiac output, blood pressure. Okay, so then between the arterioles and the left ventricular myocardium, it doesn't matter which one we put where. The order of those two doesn't matter because they're both going to be their own pathway to blood pressure. So we can put, we'll put left ventricular myocardium first. Left. Okay, how does the left ventricular myocardium respond to the epinephrine? I'll wait for you guys to answer.
Increase the contraction strength.
Increase contraction strength. So epinephrine acts on the left ventricular myocardium to cause an increase in contraction strength, which causes what?
And stroke volume.
Increased stroke volume, which causes
Increase cardiac output.
increased cardiac output, which will give us increased blood pressure. Okay, third pathway over here would be, what goes there?
Arterioles.
Arterioles. Okay, and I need to box these two as effectors. Okay, how do the arterioles respond to the epinephrine?
Vasoconstriction.
Vasoconstriction. Okay, and what does that cause?
Decreases the radius.
Decreased vessel radius. And what does that cause?
Increase in peripheral resistance.
Good. Increased peripheral resistance, which will cause an increase in blood pressure. Okay, so this is our concept map for acute control of blood pressure. This shows us in detail what's causing increases in blood pressure during exercise. Okay, I strongly suggest you be able to draw this map. Okay, may seem like a lot at the moment, but remember when we first drew carbohydrate metabolism, how complicated that seemed, and now you guys have got that down. So all you have to do is put in the work to remember this, but I'm not asking you to memorize this just to memorize it. If we were taking the test in class, I might ask you to draw this. Since we're taking the test online, it's not likely that I'm going to ask you to draw this, but being able to draw it is going to be very helpful to you, because what if I had an essay question on there that said, describe in detail 3 ways that epinephrine contributes to increases in blood pressure during exercise? So then you've got to say, well, epinephrine acts on the SAE node to cause an increase in heart rate, which causes an increase in cardiac output and blood pressure. Epinephrine acts on the left ventricular myocardium to cause an increase in contraction strength, which causes increased stroke volume, cardiac output, blood pressure. Epinephrine also acts on the arterioles to cause vasoconstriction, which decreases the vessel radius, which increases peripheral resistance and increases blood pressure. Okay, so the purpose of this map is to help you organize all of these details so that you can explain the processes. Okay, so being able to draw this map is going to make it so that you don't miss any details in that explanation. Because if I ask you to explain this in detail, I want all of these steps. And any step that you skip is going to be a point that you miss. Okay, so it's going to benefit you to be able to draw this so you can explain to me how epinephrine is contributing to increases in blood pressure. Okay, or I could ask how the parasympathetic nervous system is involved in increased blood pressure during exercise. And then you'd talk about it with drawing, which increases heart rate. Okay, so this is just an organization of a lot of information. Okay, questions on this? Anything involving acute control of blood pressure? This is, Cindy just asked what's it called? This is acute control of blood pressure, or how blood pressure increases during exercise. How does increase in blood pressure from epinephrine decreasing the radius through vasoconstriction? Okay. Okay, so Andrew wrote a question. How does the increase in blood pressure from epinephrine decreasing the radius through vasoconstriction relate with sympatholysis? Okay, that's a great question. So during exercise, we have epinephrine causing vasoconstriction. We also have, at the exercising muscle, arterioles causing vasodilation. Those things are happening at the same time, okay? But we're not putting the vasodilation on this map because it's not contributing to increased blood pressure. There are a lot of things happening during exercise that are not on this map. This map is just organizing the information for how we increase blood pressure. So yes, that sympatholysis is still happening. We're still getting vasodilation at the exercising muscle, but that's not part of the increase in blood pressure. But the vasoconstriction is contributing to the increase in blood pressure. Okay, that's a great question. Other questions? Okay, I'm going to take this map down. Make sure you screenshot it. Moving on. Okay, I'm erasing this. A couple more topics. Next one is venous return mechanisms. Whoops. What happened? Venous return mechanism. There. Okay, so venous return is referring to returning blood back to the heart after it's been at the muscle. We need it to return to the heart. But the issue is when we're exercising, our heart is pumping and it's pumping blood out to the muscles, but we don't have another heart back at our feet to pump the blood back up. And assuming we're upright, the blood has to fight against gravity to get back up to the heart. So we need some kind of mechanisms to assist with our venous return when we're exercising. Okay, so I'm going to go over 3 venous return mechanisms. First one, this is not another chart. This is a list of terminology. Okay, venous return mechanisms. The first one is skeletal muscle pump. Okay, so imagine you're walking around and these are your leg muscles. Okay, and within your leg muscles, you have these veins. So when you contract your leg muscles, it's going to compress the veins. Okay, so think about if you're holding a small water balloon and you squeeze it, but it's not full enough to pop, so you can squeeze it and the water just kind of moves around. Okay, so if you squeeze that water balloon, the water has to move out from where you're squeezing it, and it's going to move out from both directions of your fist. Okay, when you contract the muscle, it's going to compress the vein. The blood has to move out from that area as you're compressing the vein. But these vessels have valves. They have one-way valves. So the blood can only move in one direction. It only allows blood to flow up towards the heart. The valves prevent backflow. So when you contract the muscles, it compresses the vein, which forces the blood to move. The only direction it can move is towards your heart. So contracting your leg muscles assists with your venous return. Okay, I'm gonna explain that again. You contract your leg muscles, it compresses the vein, forces the blood to move. Because of the valves, the only direction the blood can move is towards your heart. Okay, so this is one of the main reasons we don't let people sit down when they stop exercising, right? If someone's been running and they sit down, they cross the finish line and they sit down, we're all trained to say, no, 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 you have to stand up and walk around, but nobody understands why. Okay, one of the main reasons you have to walk around is to activate this muscle pump. Because if you sit down, if your heart is pumping really fast from the exercise and you sit down, the blood is pumping out of your heart, but there's no activation in your leg muscles to pump the blood back up. So what happens is the blood ends up pooling in your legs. And if you've ever experienced that before, things start turning black. You might start seeing stars. And if you don't do something at that point, you'll pass out. So passing out is your body's way of assisting your venous return, because if you're passed out and you're horizontal, you don't have to fight against gravity to get the blood back to your heart. Okay, so you'd pass out, you'd fall down, blood would return to your heart and your brain, and then you'd wake up. Okay, so better would be to walk around. So you say keep walking around. That activates your leg muscles, which activates the skeletal muscle pump. So you're compressing the veins, pushing the blood back up towards the heart. Okay, so when someone stops exercising, you always tell them to walk around. If they're too weak to walk around, they can't sit. They have to lie down. And even better, lie down and put your legs up, because then you're working with gravity to assist your venous return. Okay, so you can either walk around or you can lie down and put your feet up, but you can't sit, because sitting specifically keeps you in the position where you're fighting against gravity, but takes away the muscle pump. Okay, questions on the skeletal muscle pump? How it assists venous return. Okay, second one is the respiratory pump. Respiratory pump works in a very similar way as a skeletal muscle pump, except it has to do with your breathing. Okay, so as you're breathing, you're expanding and compressing your lungs, you're expanding and compressing your thoracic cavity and your abdominal cavity. Okay, anything that compresses is going to compress the veins. When you compress the veins, it forces the blood to move. And since they have one-way valves, the blood can only move towards the heart. So as you're inspiring and expiring, you're compressing the veins, forcing the blood to move back towards the heart. Okay, if you want to think about that in more detail, if you have Andrews for 446, we'll go into this in more detail. So you have the diaphragm muscle that separates the thoracic cavity from the abdominal cavity. And as you breathe, as you inspire, the diaphragm moves down, and we're going to talk about that in detail in the next chapter, which is respiratory control. But as you inspire, the diaphragm moves down, which compresses the abdominal cavity. If you compress the abdominal cavity, it's forcing the blood to move up. Okay, then you expire, diaphragm moves up, compresses your thoracic cavity. That's going to compress the veins and force the blood to move to the heart. Okay, so the inspiration, alternating between inspiration and expiration, compresses the veins, moves the blood towards the heart. Okay, questions on that one?
You said alternating between inspiration and expiration?
Yes.
Okay.
Yeah, it shifts the pressure from the abdominal cavity to the thoracic cavity, which forces the blood to move. Okay, third one is vasoconstriction. So if you think about spraying water from a hose, you cover half of the opening with your thumb and the water shoots out more forcefully, right? So the narrower the vessel, the more forcefully the blood will go through. So as you're vasoconstricting during exercise, the blood is going to be pushed more forcefully through. And all the vessels are connected, right? So at some point, that's going to assist with venous return. Okay, vasoconstricting the vessels increases the pressure with which they go through, the blood goes through, which will increase venous return. Okay, so you need to be able to name and explain these three venous return mechanisms. Questions on those?
Sorry, did you say for the vasoconstriction, the narrower the vessel, the faster it'll?
Yes, the more forcefully the blood goes through as the vessel narrows. Mm-hmm.
And that's only for the arterioles, right? Like not
Correct.
for the veins.
Correct. The veins don't have muscles, so they can't dilate and constrict.
Professor, can you explain the skeletal muscle pump again?
Sure. So skeletal muscle pump, as you contract your leg muscles, it compresses the veins. Compress the veins, the blood has to move. And because of the one-way valves, the blood can only move in one direction, and that's toward the heart. So compressing the veins moves the blood towards the heart. Contracting the muscles, compresses the veins, moves the blood to the heart. Okay, last topic we're going to cover today is blood. Let me clear this. Three functions of blood as it relates to exercise. Transportation. Transportation of nutrients. So our glucose and our free fatty acid and our amino acids are our nutrients that are transported in our blood. Temperature regulation. So our blood helps us with temperature regulation by moving towards the skin. Remember, we have vasodilation in the vessels near the skin during exercise so that we can dissipate heat and so that we can sweat. So our blood is related to temperature regulation and also pH balance. The pH is the acidity of the blood, and the bicarbonate buffer is in your blood. So the blood helps us control our pH balance. Okay, so these are three functions of the blood as it relates to exercise. Okay, then we'll talk about components of the blood. So if we were to take out a vial of blood and spin it in a centrifuge, it's going to separate into its different components. Okay, the two components of the blood are formed elements. Formed elements are mostly red blood cells. There are also white blood cells and platelets in there, but we're mostly concerned with red blood cells because that's what has the hemoglobin, which carries the oxygen, which is going to be related to our exercise capacity. Okay, so formed elements, mostly red blood cells. That's the thicker portion of the blood. And then the rest of the blood is plasma, which is mostly water. Okay, then we have hematocrit. Hematocrit refers to the thickness of the blood. So it's what percentage of your blood is formed elements. So if you have a higher percentage of formed elements, that means your blood is thicker. So you have a higher hematocrit. Okay, so the hematocrit refers to what percentage of your blood is formed elements. So go back and think about how we find your percentage on the midterm. It's the points, the number of points you earned divided by the total amount of points possible. Okay, so to figure out what percentage of your blood is formed elements, we would say hematocrit equals formed elements divided by total blood volume. Total blood volume is all of this. So formed elements divided by total blood volume tells you what percentage of your blood is formed elements. Hematocrit is not expressed in percent. So it's not going to be multiplied by 100. It's just going to be a number. So normal hematocrit is 45. Go ahead. Somebody have a question? So normal hematocrit is 45, which we know means that 45% of your blood is formed elements, which means that 55% of your blood is plasma. But we wouldn't say hematocrit is 45%. We just say hematocrit is 45. Okay, but we know that it's an expression of percent of formed elements. Okay, we okay with that terminology? Hematocrit is related to viscosity. Remember, viscosity is thickness of blood. Hematocrit is related to the thickness of the blood. The higher your hematocrit, the higher the viscosity. So as hematocrit goes up, viscosity goes up. Viscosity is related to peripheral resistance, which is related to blood pressure. Okay, so all of these things are going to connect. We're not going to get that far right now, but I just want to talk real quick about how we can affect our hematocrit, make it go up or down. So formed elements, red blood cells, that means if your red blood cell count goes up, if your plasma stays the same, but your red blood cell count goes up, that would be an increase in formed elements, would be an increase in hematocrit. So one way you can make that happen, hold on 1 second. Let me take this down, is to do altitude training. So when you do altitude training, the issue at altitude is that it's harder to get oxygen into your blood. I'll explain why in the next chapter when we get to respiratory control, okay? But at altitude, it's harder to get oxygen to move into your blood. So your body responds to those conditions by producing more red blood cells so that you have more hemoglobin so that you can carry more oxygen. So if you train at high altitude, you're going to produce more red blood cells. Then when you go down and compete at sea level, you have more red blood cells than normal, which means you can carry more oxygen, which means you can consume more oxygen. So it's going to improve your endurance performance significantly, which is why people do altitude training, or I can't think of the word. They simulate that with the mask. So without going to altitude, you wear the altitude mask and it restricts your oxygen. So it creates the same conditions, which would trigger your body to produce red blood cells, which would then improve your endurance performance. Okay, but that only works if you've been training so that you have the other adaptations of the mitochondria and the myoglobin and the capillaries and the enzymes. If you don't have all those adaptations and you're just increasing your red blood cell count, you're not going to have the capacity to consume it in the muscle. So you have to first do all the training to get those adaptations so you can consume the oxygen. Then you do the altitude training to increase your red blood cell count, and then it's going to improve your performance. Okay?
Does that only increase red blood cell count or all formed elements?
We're specifically talking about red blood cell count.
Okay.
Yeah, and I'm just noticing that I went overtime. When I go overtime, you guys can let me know, because I'll just keep talking.
It's okay.
Sorry about that. So I'll stop there. You guys have to remind me where I stopped. I just have a tiny bit more in this chapter, and then we'll be moving on to the next chapter. Okay, do you have any questions on any of this? or anything else? Going to your workshops? Office hours?
I do have a question.
Go ahead.
It's not really on this topic, but
Okay.
on our workshop, we were actually wondering where does the inorganic phosphate accumulate?
In the sarcoplasm. Yeah, that ATP is just being broken down in the sarcoplasm. But remember, the sarcoplasmic reticulum is right there within the sarcoplasm. So it's going to be affected by the phosphate. All right, I just want to remind you guys, if you have Tuesday classes, tomorrow is a holiday. It's Cesar Chavez Day, so there shouldn't be any classes happening tomorrow, as far as I know. So if you have a professor who's having classes tomorrow, you might want to remind them it's a holiday. Someone just reminded me. So.
And that's the same for the PLFs, right?
Yeah, there shouldn't be anything happening tomorrow. So if
No,
Tuesday's your normal workshop day, you need to find another one for this week because there's no school tomorrow.
Cool.
I mean, they can have a workshop if they want to out of the kindness of their heart, but it's
No, they can have an email
holiday.
saying they cancel for Tuesdays.
Okay, yeah, it's a holiday, so there shouldn't be any classes happening. Okay, I'll stick around for a minute if you have a question. Otherwise, I will see you guys on Wednesday.
I had a question.
Yeah, go ahead.
Can you just go over the respiratory pump one more time?
Sure. So you can just think of it as you inspire and expire.
Mm-hmm.
The veins are being compressed. And if you compress the veins, the blood has to move. And towards the heart is the only direction it can move. So breathing, inspiring, expiring increases venous return.
All right, thank you.
You're welcome.
Professor, can you explain why vasoconstriction is good for venous return also?
Sure. So vasoconstriction, as the vessel gets narrower, the blood is going to come out of that vessel more forcefully. So since all the vessels are connected, if we start pushing the blood more forcefully, it's going to end up assisting with the venous return.
Professor, you know, like the formulas that we went over, how can you ask that in a question of how it connects with each other? That makes sense. Like, never mind. That's okay. It's okay.
Well, in knowing the formula for stroke volume,
Yeah.
you have to understand end-diastolic volume and end-systolic volume. Okay, and that's going to be part of cardiac output, right? Because cardiac output is heart rate and stroke volume, so we could expand that one as well. So end-diastolic volume and end-systolic volume are part of stroke volume, which is part of cardiac output. So that relates those. And then cardiac output is part of blood pressure. So all of those end up being connected. But yes, you need to know all those formulas. Go ahead, Andrew.
Sorry, did you go over why decreased viscosity is beneficial to performance?
Yes, I'm going to cover that in the next lecture, but I can go over it real quick right now if you want.
Okay.
Say the question again.
Why is decreased viscosity beneficial to performance?
Okay, so viscosity is related to hematocrit, right? So as hematocrit goes up, viscosity goes up, which means resistance goes up. Think about that as resistance to blood flow. So the thicker your blood is, the more resistant it is to flow. So if you think about the opposite, the thinner your blood is, the lower the hematocrit, the lower the viscosity, the lower the resistance. So the thinner your blood is, the less resistant it is to flow. So we'll get more blood flow to the muscle if the blood is thinner. That will improve performance because we'll be able to deliver more oxygen. Yeah, we'll talk more about that in the next lecture. We didn't quite finish that topic.
Is the Monday, Wednesday, sorry.
Go
ahead, Esmeralda, go ahead.
So for example, like distance training, would it be good to also include altitude training?
Yes, but only right before the event because you're not going to maintain those extra red blood cells while you're at sea level.
If we go back to the inorganic phosphate, how exactly does that cause the fatigue?
Inorganic phosphate accumulation inhibits calcium release.
Oh, okay.
So if we have less calcium released, we have fewer cross bridges and power strokes, less muscle contraction.
All right. Thanks.
Mhm. Anything else, guys?
Oh, for the intrinsic control of blood flow, was it just the chemoreceptors sensing the decrease in O2, increase in CO2, and accumulation of lactic acid?
There should be
There
six.
were other
There should be six
yeah.
factors there. Yeah.
And then for
Triggering vasodilation.
For extrinsic, it would just be epinephrine.
Mhm. Acting on the arterioles to cause vasoconstriction. Mhm.
Okay. Thank you.
You're welcome. All right, you guys, if you don't have any more questions, I will see you on Wednesday. Bye, have a good day.
Thank you.
Thank you.
You're welcome.